This is the third in a series of resources that look at matrix algebra. We define and provide basic information about matrices. We consider the operations that allow us to manipulate matrices. We discover how to use the row operations to solve a system of equations using matrices. We consider various operations on pairs of matrices, including adding, subtracting, linear combinations, and multiplying. We learn how to find the inverse for a matrix. We discover the determinant for matrices and learn how determinants allow us to solve systems using Cramer's rule. In the last resource, we discussed the three row operations: row swap, scalar multiplication, and linear combination of rows. We also said they were the means for solving a system of equations using matrices. This resource will provide the methods for doing exactly that. Ultimately, we want our matrix in reduced row echelon form. This form has ones on the main diagonal from the top left to the bottom right positions, and zeros everywhere else. Once this is accomplished, we can just read off the solution. X would equal A, Y equals B, and Z equals C, if there are three variables. But how do we get into reduced row echelon form? First, we need to put our system of equations into the augmented matrix. Next, we try to get a 1 in the upper left position. We use either row swap if there is a 1 in the first column, or scalar multiplication if there is no 1 in the first column. Then we use linear combinations to make the values under the 1 go to 0. In each case, we multiply the row with the 1 by the opposite of the value we want to go away. Next, we get a 1 in the next position down the main diagonal, using either row swap or scalar multiplication. Note that we will not move row 1, as we want to keep the 1 in top left. Then we use linear combinations to get zeros underneath the 1. Repeat this process until we have 1s down the main diagonal. Then we work from right to left to get zeros above the 1s. Let's see an example. Suppose we want to solve the system of equations 2x plus 4y equals 38 and 3x plus 10y equals 77. First, we need to set up the augmented matrix. We put the coefficients on the left side and the constants on the right side of the vertical bar. We want to get a 1 in the upper left corner. Since there are not any 1s in the first column, we will use a scalar multiplication to get our 1. Multiplying row 1 by 1/2, we are left with 1, 2, and 19, then 3, 10, 77. Now we want to get a 0 underneath the 1 we just created. We need to make 3 go away. We will multiply the row with the newly created 1 by the opposite of 3, -3. We do the linear combination -3 times row 1 plus row 2. -3 times 1 plus 3 equals 0. -3 times 2 plus 10 equals 4. -3 times 19 plus 77 equals 20. Next, we need a 1 in the bottom right corner. We will multiply row 2 by 1/4. This leaves us with the matrix 1, 2, and 19, then 0, 1, and 5. To finish our work, we need to make the 2 above the newly created 1 go away. We will use the linear combination -2 times row 2 plus row 1. -2 times 0 plus 1 equals 1. -2 times 1 plus 2 equals 0. And -2 times 5 plus 19 equals 9. So the solution to the system of equations 2x plus 4y equals 38 and 3x plus 10y equals 77 is x equals 9 and y equals 5. Let's see an example where we have 3 variables. Suppose we want to solve the system of equations 2x plus 4y minus 9z equals 5, 5x plus 7y minus 17z equals 12, and x plus y minus 3z equals 2. Let's solve this using a matrix. First, we need to put the system into an augmented matrix. We place the coefficients on the left side with columns for x, y, and z, and the constants on the right side of a vertical line. We need to get a 1 in the upper left corner. We could use a scalar multiplication, but we already have a 1 in the first column. We just need to swap rows 1 and 3. Now we want to get zeros under the 1 we just created. 1 is such a handy tool in mathematics. We will use linear combinations involving row 1 to make the 5 and 2 below it go away. The exact linear combinations we use are -5 times row 1 plus row 2, and -2 times row 1 plus row 3. For row 2, we have -5 times 1 plus 5 equals 0. -5 times 1 plus 7 equals 2. -5 times -3 plus -17 equals -2. And -5 times 2 plus 12 equals 2. In row 3, we have -2 times 1 plus 2 equals 0. -2 times 1 plus 4 equals 2. -2 times -3 plus -9 equals -3. And -2 times 2 plus 5 equals 1. We want a 1 in the middle of the matrix. We will do the scalar multiplication 1/2 times row 2. This leaves us with 0, 1, -1, and 1 in row 2. The other rows stay the same. We want to get 0 under the new 1. We use the linear combination -2 times row 2 plus row 3 to do so. -2 times 0 plus 0 equals 0. -2 times 1 plus 2 equals 0. -2 times -1 plus -3 equals -1. -2 times 1 plus 1 is -1. Now we want a positive 1 in the bottom right position. We multiply row 3 by the scalar -1, and we are left with 0, 0, 1, and 1. Now we hit will work to fill in the top half of the matrix with zeros above our 1s. We start in the rightmost column. we will use the linear combinations 1 times row 3 plus row 2 and 3 times row 3 plus row 1. We have a lot of zeros going on, so we will focus on the last two columns. For the second row, 1 times 1 plus negative 1 is 0. 1 times 1 plus 1 equals 2. For the top row, 3 times 1 plus negative 3 equals 0. And 3 times 1 plus 2 equals 5. We finish by needing 0 in the middle of the top row. We use the linear combination negative 1 multiplied by row 2 plus row 1. Again, lots of zeros. But we have negative 1 times 1 plus 1 equals 0. And negative 1 times 2 plus 5 equals 3. The solution for the system of equations 2x plus 4y minus 9z equals 5, 5x plus 7y minus 17z equals 12, and x plus y minus 3z equals 2 is x equals 3, y equals 2, and z equals 1.